Okay, so this is 5-axis post-processing, August 2017, day 4, section 2. So we're just returning from break. We've got the vector directions now set up to give us good code. And we can tell with this single curved 5-axis toolpath. Again, this is, looking straight down at the platter, or actually if this was already rotated to -90, looking straight at the platter. The tool right now is shown rotating. There is a trick in backplot. If you go into the backplot settings, and you do simulate rotary axis, now it's not doing it with the vector-based toolpaths. So with the other toolpaths, you can get it to show the part spinning around on the screen and the tool remaining stationary sometimes. Turn off simulate rotary axis. So yeah, it used to work that way, and I think it used stopped with 2017. I don't know. Yeah. I see it jumping around. I don't see it really doing what I remember it doing, which was actually showing the part spin. Now, it used to be, at least in X9, that it would use at least one of the rotaries, and I can't remember if it's the last rotary. The problem is, it says simulate rotary axis. It's only for 4-axis rotation, and we've got a multi-axis toolpath with vector lines. And that's different from a contour where we're doing axis substitution. So, anyway. I'm not even going to worry about the backplot settings and stuff. Let's look at what we've got here for this set of toolpaths. If we go into backplot. Wait, what were you saying? Open the dialog. You select the rotary axis. Oh, in curve. Under tool axis. Backplot rotary. There we go. So backplot rotary axis, we're going to do it about Z. Let's regen that. Good tip. There we go. So now, if we go into backplot and we say simulate rotary axis, there we go. So that's basically what we're going to see, with the exception of this rectangular piece not moving, because that's part of the A-axis trunnion. Thank you for that, actually. I knew it used to be in there. So what else do we got? If you look here, I've got a toolpath that's using the back plane. I've got a toolpath using the front plane. I've got one on the right side, and I've got one on the left side. So this is another very simple test we can do. And what are we looking for here? With a Trunnion style setup, most of the time, the rotary zeros have the part facing up on a platter like this. So when we first start out, this, if we were looking in the top of the machine from the spindle, our part would look like this. It's sticking straight up towards us. So with our default planes, top, front, back, right, and left, we should be able to get 90-degree rotation of the primary axis after we've tilted. So the order in which we have our operations and the order in which the tool planes are used can sometimes affect whether or not we're starting at 0, right? So if I look at this toolpath on the front, in order for my tool to reach this side of the part, we have to first rotate to -90 because we have a limited travel range on that secondary axis. And then, because the tool, you can see here, is upside down, we're going to have to end up rotating 180. Now, there's nothing inherently wrong with that, okay, with that being C180. In fact, for the front plane, that's the proper rotation for this C axis. But if we're just starting out and we throw this path down as our base path, we really have to think about the order in which our tool planes are directing the trunnion to move. Because there's nothing wrong with this being your first tool path, but just realize that it's going to be at C180. And if you wanted it to be at C0, well, then you should have used this back tool path. That plays into part orientation. In general, when you're using the Generic Fanuc 5x mil post, I highly, highly recommend that you take your part and you move it back to the system origin. There is a lot of stuff internally inside the post that assumes that we're using the system top for the orientation of our spindle at 0. The one exception to that is if we make a change to the machine base matrix. So the machine base matrix tells us essentially how is our spindle oriented in 3D space, and everything flows out of that. So if we do have a horizontal 5-axis, we need to change the values here, and they actually, you can see, give you 2 columns, HMC and VMC. 100, 010, 001, that is the standard 3D WCS gnomon. So if we look at the top plane, these 3 axes and their orientation to each other are controlled by the relationship of these 9 numbers. Jeremy says, so you're saying not to use WCS. Yes, that is my recommendation with this post, with the Generic Fanuc 5X post. You can try creating the WCS out there in plane space and then creating your planes relative to that. Lots of people are successful doing it. I just know that when you're trying to do debugging and you're way out in the middle of airplane coordinates with your WCS, it's just one more place for something to go wrong. If you create your geometry and measure things as they exist in the real world and use that as the setup with your WCS in the proper spot, then both 3+2 operations and 5-axis operations. No, well, I don't just mean for debugging. I mean, as a recommendation in this post, this is the way that the generic Fanuc 5x mill post is set up. And so here's my thing. They keep breaking the planes. So a lot of my caution and recommendations, honestly, Jeremy, come from having used Mastercam for 20 years and having had problems in the past with different versions of Mastercam and the way that it interpreted planes and having some serious bugs. Now, starting in X7, they started rebuilding all of the underlying architecture to the planes dialogue, and this guy, Ray, who, brilliant guy, super brilliant, spent the better part of a year and a half going through the database and tearing out all of these different functions that were related, but that ended up manipulating different. So a lot of this, is my recommendation from, again, having been burnt in the past by these issues. Now that Ray has gone through and rebuilt all of the planes, they should work better. But also I also take it, with a grain of salt, and like most people, I'm slow to trust again once somebody has burned me. So for me, I recommend always bringing the part back to the system top view, because it's one less thing that you have to worry about. Basically, there's a translation and a rotation happening with your coordinates whenever you're out in plane space. And all of this stuff is tied mathematically together with a set of tolerance values, right? So how accurate is everything? And now if you've taken all this geometry and you've now rotated it and translated it in space, now is all this stuff relative to that new plane, or is this all relative to the Mastercam world? Well, they'll tell you it's supposed to work with the WCS, but these are some of the kind of problems that have cropped up in the past. It will simplify your life greatly. Yeah, and so you'll see that as well with things like older operations that had the database built in a certain way, and now you're bringing them into the newer version, and all of a sudden, for whatever reason, it's creating all these new planes and assigning them to your operations. And if it's just the tool plane, it's not great. You still have to regen the operation. But if it changes the WCS on you, you might accidentally get the wrong work offset, scrap the part. There's all kinds of things that could happen when you start messing with something like a plane, because there's so much that's tied to it. So, especially for people that are just starting out, I recommend moving stuff to the system origin for 5-axis work. It'll just make your life easier, especially if you have to swap out a different machine. So sometimes you can have it where you've got a set of toolpaths for 5-axis set up, and the operation itself has or at least had in the past, machine settings, and they may have moved those out. Yeah, because they've just got this backplot axis now, but depending on the operation as well, because this is curve, so this isn't the something like one of the module works toolpaths, but there is some logic that exists in Mastercam for replacing machine definitions. So this is a good thing to know and a good trick to learn if it ever happens to you. And this logic will look at the configuration of your rotary axes and will make a determination if your machine is compatible with the toolpaths that you have in here. And depending on compatibility, it will either gray out the operation and not let you use it, or in some cases it will not even let you make a replacement on the machine definition. So the way to defeat that is to make sure that you've got a rotary axis for all three different axes of rotation. And in those cases, so I've got an A and a C here, and what we end up doing is going VMC, B axis, and I'll just put that on Z. So we're rotating about Y, and really, this is just a dummy axis. And by adding it, this axis combination is now able to achieve vector positioning for every conceivable toolpath you could possibly throw at it. The thing is, in order for this trick to work, we now either have to diligently create and use axis combinations, or we have to be aware that we've got this extra axis in there and know how that would affect the toolpath that we're creating, because that could cause an issue. So if you have an issue with that, I would end up creating a new axis combo, which is correct. So X, AC, mill table, Y, Z, and then VMC tool spindle. Whatever is listed in top in the list, whatever's listed in the top here will be the default. Okay, maybe put a little warning in there for some other programmer. The purpose of having an axis combination with A, B, and C is that there is logic in Mastercam that is invoked when you do a replace on a machine definition. So if you replace a machine definition that was an AB configuration with one that is a BC or an AC, sometimes due to the orientation of the vectors in the toolpath, Mastercam won't let you make the replacement. And by creating this fake dummy 6-axis axis combination, we can kind of trick Mastercam into saying, hey, you know what? Allow us to do the full replacement with this machine, because there is an axis combination present that could potentially reach any vector that we might generate. Okay, so getting back to our example that we were working on, we've configured M-type. It was already set to 0, so it's not like I did anything here, but I left it 0. I didn't change it to the wrong one, I guess. And we've got our vector directions set. If we now take these 5 operations, make sure they have the same NC file name here, and then we post them. Oh, and you'll also notice I actually have a tool change, and then, so a tool change to the first tool here that's new, a tool change back to 256, and then I have 2 null tool changes. So these are operations where the tool repeats. And what I get is C0A90, which is what I want, right? We've got our table tilting towards the operator at -90, and we're approaching the part. Now we're feeding in, and then we're rotating. And with our rotation, is counterclockwise, and it's going positive. So it goes positive, winds up all the way to 360, retracts. Then we get the machine going home. So it retracts to Z9 as part of the operation. All of this, M5, GO, G28, G91, Z0, G28, C, and A0, all of that is a post-generated move. So when we look in our post, there are some default post blocks that we need to be aware of, and we're going to start looking at these kind of starting next week. So after we get down through the configuration and all of the string select tables, we come to the first sections of output. Tool comment, manual entry. So comment for tool, P tool comment. All of this code here is what's going to be used to create tool comments at tool change. P tool table. This post block is what creates each line inside our tool table. P tool comment, or P comment 2, is where all of the different comment lines get processed. And we'll come back to this one a little later when we look at some modifications we may want to do for manual entry. Then we come down to start a file and tool change setup. When we first kick off the start a file and the tool change, we actually call P header. So as I scroll down here, this is where the actual start, very first characters and the start of the file for the NC program start to occur. So P header is what gives us all of our date and time information, information about the Mastercam file, and then in between our header information and the actual start of file characters for the first tool change. So PSOF is always the first tool change. In between there, we're going to get our tool table. And we get the tool table output because there is this mechanism in MP that will create a tool table if you tell it to. Basically, when tool table is set to 1 or 3, then MP is going to go through some extra routines to generate a tool table. And it makes these calls to PWRTT. All PWRTT does is look to see if tool info is turned on. It looks to see if this is the first tool change to a new tool number, and it looks to make sure we're not at the end of the file. And as long as those three conditions are true, we call P tool table. There is a special mechanism in MP that keeps track of every tool number that's being used. The first time a tool is used, the tool is signed positive. So if I use tool 5, the first operation that uses tool 5, when we call PWRTT, T $ is going to equal positive 5. So it's going to be greater than 0, and we're going to call P tool table. Every other time that I call tool 5, MP will sign it negative. So there's this special thing that happens where T $ gets signed negative for a tool that repeats. And what that means is that you only get one entry in the tool table for every tool. You can change that behavior by removing this condition and then writing logic in your tool table to look and see if the offset number is different and do some other things. But that's how this works by default. We have two parameter sections. PWRTT params. This is a post block that is used to capture parameter data during the tool table output. So if you want to put data in your tool table, generally you need to capture it here in PWRTT params. P parameter is used to process parameters during normal output. So if you want to grab any parameter data while you are processing a regular tool change or motion G code or whatever you're doing, as long as it's during normal output, we grab the data in P parameter. There's a lot of stuff that happens in P prep inside this post. A lot of capturing of variable values and updating of variables. The generic Fanuc 5xmil post uses a lot of comparison between current values and previous values. And it also stores data in previous values of variables. So whenever we look at a variable, MP creates two data slots for every variable. It creates the current value slot and it creates the previous value slot. And the mechanism that normally shifts one to the other is modality. So when a variable gets output to the NC code, we automatically update the previous value. That's the way MP normally works. For the 5-axis post, that is not true. The generic Fanuc 5xmil post has a special command variable called no update previous, and it's turned on. And what this means is that even when a variable value is output, so we write a line of code that has an X and a Y position. Normally when that occurs, we would then automatically take the current position of X and the current position of Y and move them into the previous variable slots. That doesn't happen here because there is logic inside the bin portion that does all of the variable updating based on the timing of the event. So are we prior to the move? Are we in the move? Are we after the move? And there's logic to update all these variables internally. So I just wanted to point that out. Wanted to just kind of touch on a couple of those blocks. Starting next week, we're going to get into making edits to the NC code. So far, this has primarily been about understanding how to configure the post based on these variable settings. Because honestly, guys, this is like 90% of editing the post. You got to set up these variables right. And once you get them set up, then yes, you can add logic to do all kinds of different stuff that you may need. But if you're driving a Fanuc machine, I mean, honestly, this code will drive most Fanuc machines. You may want stuff for high-speed codes or different modes to be turned on and off, and we'll talk about doing all that stuff. But it's also important to just be able to get here, right? Just to do the base configuration for a 5-axis post and know how to change these, vector settings when you need to. So before we wrap up class for tonight, let's just go through some more of these setup variables. There's a special one down here. Drill use clearance. Use drill clearance plane at the start and end, read from toolpath parameters. So what this does when set to 1 is it forces a retract to the clearance plane at the end of a drill toolpath. By default, there was some this is a fix that was put in for a bug that was in the NCI, where you would turn on a checkbox to say start and end at the clearance plane for a drill toolpath, but you only had 1 point. So the error only occurs when you were drilling a single drill point, and it wouldn't output the clearance at the end. And this was a switch to get around that. Use tool length. We're going to set to 0, which means use the tool length variable. And in our case, the tool length variable is 0. We're not going to shift by the tool length because this is a table style post. And I believe we want, for break move head, we want to set this to 2, which is tooltip programming. Normally this isn't used for table, but we'll do this just in case. We don't know what the axis shift values are yet. We'll come back to the break move head here in a minute. And rotary axis limits adjust to secondary. We definitely want this on. So basically it will allow the primary to flip 180 degrees when the secondary is out of position. And the reason we want this on is because with our post, our secondary is fairly limited. We've only got 150 degrees of travel. We've got negative 120 and we've got positive 30. So let's go set that. Now in this case, we're probably going to allow the primary to wind up. We can still allow the primary to wind mathematically, but restrict the output to 0 to 60. So there's a separate switch for doing that. So what we're going to do is we're going to allow the rotary to wind up. So I'll do 7 nines for the primary. On the secondary, we're going to do minus 120 and positive 30 for both the intermediate and the absolute angles. Spindle align is set to Z+. That's the way that our spindle is aligned if we're looking at the rotary facing up towards the spindle. Now that we've set the primary to be allowed to wind up, we can address the output. And the output is taken care of with these guys here. P AUG output and S AUG output. We can use normal angle output for the secondary, because we've already got an axis restriction that limits us to only 150 degrees of travel, but we still want to be able to use plus and minus. If we use implied shortest direction, we don't get any negative value at all. Implied shortest direction only puts values between 0 and 360 positive. So that won't work for here, for the secondary. We could use number 1, which is signed absolute output 0 to 360, but we're never going to have the secondary wind up, so whether we use 0 or 1 for the secondary doesn't matter. I'm going to leave it 0. The primary, however, is where we need to test the machine. So when we look, it tells me the C-axis travel is 360. But is that only 0 to 360 no matter what? Or is that plus or minus 360? In other words, will it take a negative value to rotate the opposite direction? This is something we need to know, because if it can't wind up, we can't do any continuous move over 360 degrees. Now, this is something that the programming manual for the machine should tell you. You know, what is the actual rotary travel limit for the C-axis table? And we won't know until we, really investigate a little bit more about the machine. Right now, we can at least tell it. I would at least do signed absolute output 0 to 360, because we know we're limiting the output just by it saying it's only 360 degrees. This would at least give us plus or minus 360 and allow the table to rotate the opposite direction by being signed negative. If I put a 2 in here, that is going to, again, I wouldn't be doing that for the secondary, I mean for the primary. So if I put a 2 in here, implied shortest direction, absolute output, that's going to limit us to only outputting positive values, and it will mean, whether we go negative or whether we go positive, it calculates the distance to go, and it just outputs it as an absolute 0 to 360 value. This is really the more limited of the options. If it can't take a negative value, but that's what you have to do, is set it to 2. For now, we'll set it to 1. So we've set our travel limits, and this just says let the primary wind up to this many absolute rotations, which is 27,000. So we can basically wind the axis up 27,000 times. Let's take a 0. Let's take a 9 off of there, which makes it like 2,700 rotations. So we'll change those settings. And we'll post it out. So this didn't change. Still starting negative 90, C0, and we're rotating positive. We get all the way to 360, and we do our retract. Now we're starting with our new operation here. So this code is all coming from the tool change. We've got the startup codes here. We're telling it to retract to absolute Z. We're changing the tool. So T241, M6, G0, G56, G90. Huh, okay. So if I go back and I look at tool number 1 here, I'm getting G54. If I look here at the second tool change event, I'm getting G56. And if I go to my next operation down here. Okay, I'm back to G54. And here's G55. And here's G57. So what I need to go do is look at my planes. And you can see here, this is actually what I've got set for my offset values. So each plane here is set manually to a specific work offset. If I want them all the same, I can change them in here. And if I post it out, and this is what we get. Nick's got a question. Why would you want to reduce it if it is infinite? Because sometimes, even though the C-axis is infinite, its display will only display 0 to 360. And if that is the case, when you cross over 360, it just goes back to 0. So really, it's just better to see that in the code, because then you don't have to do the math and say, oh, it's, 13,284 degrees on my C-axis, but really that's, 224 on the display, or whatever. And really, it's also about, have it rounding to 360. Really, you need to look at your machine programming manual and see what the limits are and see what kind of values it accepts. That's really what those settings have to do with, is will it accept those numbers or not? Now, I'll tell you, if it only has 360 degrees of travel, if that's all it will allow as an absolute, then we would definitely set these down here this way. Okay. Ooh. So we've got these set. For the secondary, we are allowing it to wind up. You know what? I'll just set it to normal output for now. We'll set it to normal so we can see it wind. So we look at the output again. We should have the work offsets set correctly and working, which basically means we're going to call out G54 at the top. And we've got it set to force out the work offset at every tool change. Otherwise, if it doesn't change, you wouldn't see G54 repeated here. And you'll notice down here, we have a series of 3 toolpaths. This is the first toolpath. Well, it actually starts right here. So this is the first toolpath, and it makes a cut here at C180, A -90. Then you'll see that all we did was we retracted the Z-axis Yep, you're right. So there is one that got set to G57. So it must be this last one here. Yeah. Good catch. So rotate C270, rotate C90. Now, look at where we ended. So over here, we did a G3 move, and we ended at minus 1.5 in X and minus 4.25 in Y. Then we picked up 2 inches, and we rotated C270. So we were at 180, we rotate 90 degrees. And our first X position is X positive 1.5. So what do you think is going to happen here? Hopefully we don't clip this corner. You know, it looks like we're out in front of the part and away from it. But that's a bad scenario. That's a dangerous thing to do sometimes. With a trunnion, you can probably get away with it. With a 5-axis head or a head table, you're probably risking a crash by having this series of operations where the retract isn't very much. So one of the things that this post has built in is a function here called break move head, and this allows the 5-axis to create intermediate tool position vectors in between the last retract position and the next start position of the next toolpath. Right now it's turned off because if it says break move head maximum angle move, this is the break max angle, applied if chordal calculation angle moves are greater. So negative disables. So setting both to 0 disables it too. So if we set this to 1 and we set this to say 5, here's where this path ended, and here is where we make our 90-degree move. But you notice as we're moving C, we're also moving X. And this extra output is caused by this break head feature. So it used to be something that was on by default, and the silly thing, in my opinion, was that this was the default. So on a Trunnion style machine, people would go in and they'd say, oh, okay, I'm on a Trunnion, so all I really need to worry about is making sure I've got enough clearance. So if I go clearance 6 inches incremental at the start and end of my op, looking at the size of this thing, that should probably be okay. 6 inches here, and I'm thinking everything's all awesome, right? Because I'm retracting up high enough, or maybe it's not 6. Maybe it's 15. Okay, we'll make sure we go nice and high. Regen that. That looks pretty good, right? We'll retract up nice high 15 inches. And then we post it, and we get this. Remember, this is a Trunnion. So here's our C rotary. Here's our first tool change. Everything's good. Here's our next tool change. And we've retracted up high, but look what happens. All of this was used to rotate at 90 degrees. Totally unnecessary. Now, these extra positioning moves when you're dealing with a head-head, they're sweet. They help to what we call fan the head to make sure that you're not getting these jerky, abrupt motions. Because if you tell it to move 15 inches in X and move the C axis 90 degrees, you're likely to smack the tooltip into the part or in the table when you're dealing with a gantry machine. Whereas this will actually move it in a much more controlled manner. But you don't want that on in most cases for a Trunnion style machine. It's important to know about it, but it's also important to know how to turn that off. So if you happen to grab an older version of the generic Fanuc 5X mill post or the generic Haas VFTR post, these are turned on. And if you don't know about it, you start looking at your code output going, what is all this extra crap? Okay, so we turn those off, save it, post it. Okay. So C0, A negative 90, we cut around the circle, we go to CO, A negative 90, we make a cut, we go to negative 90, C180, we make a cut. Now we go up to Z 16 inches and then we just rotate. So we rotate C270, we're still in rapid mode. So now we come down here, so we move over to our position, and then we rapid down to Z1, and then we start feeding and we make our cut. We rapid back up, we rotate C90, we feed to our, or rapid to our start position in X, rapid down in Z, make our cut, rapid back up, and we're done. Okay? So, good little test program. I'm going to go ahead and save it and open for questions if there are any here at the end of class. So next Saturday, this coming Saturday, we'll be doing our regular early afternoon, late, I want to say late morning for you guys out on the Pacific coast. So it's 3:30 p.m. Eastern time start, which would be 12:30 p.m. if you're on the West Coast. Okay, so hope to see you guys on Saturday. We'll be going over Mike's other Trunnion. So that was a BC configuration. Whether or not the addresses are B doesn't really matter, but we'll get to that. And he was kind enough to provide me with some info, so we'll be going over that basic setup as well. So that'll be another nice refresher, right? Because we're going to do essentially the same thing. Nice, simple setup. Make sure all the vectors are set, then make sure all the rotaries are set, and then do all the last bit of configuration. Yeah, AC. So it's an AC, but is it rotating on Y? Wasn't that the tricky thing about it? No, wrote on X. Okay, that's fine. Yeah, so whatever the setup is, we'll get that one set up too. But yeah, and then we'll start looking at actually modifying the code. You know, how do we modify things like the tool change event? Where do we go to make our changes? What can we change? What does the post automatically track for us? So we'll look at setting up things like different coolant codes, setting up the few remaining miscellaneous integers, because if you notice, when we use the generic Fanuc post, most of these values are already used for us. absolute or incremental. There's a switch here. So basically, miscellaneous integer 1 is open for use. Reference return chooses whether we get a G28 or a G30. G28 typically being machine home coordinates, G30 typically being a user-defined tool change position. We can modify the reference return to either support machine coordinates, G53, or in some cases additional reference points, so G30, P1, P2, P3, P4, stuff like that. The rest of these guys, MI4, MI5, MI6, MI7, MI8, MI9, and MI10. All the rest of these do actually function and provide us functionality that will allow us to change output based on our settings. So really we want to leave those alone. So 4 through 10 on the integer side, I wouldn't try to modify. We do get 3 miscellaneous real values that are completely open. MISC Real 3, MISC Real 4, and MISC Real 5 are available for you to add functionality. MISC Real 1 is the approach and retract clearance distance for the vectors whenever we do like an unwind move. Right angle head is controlled by MR2 and MR10. We have the Safe Z retract, which I'll show you how to set up. We got to make sure some additional things are turned on in order for this value to be used. And MR7, 8, and 9 can be used for other things. The default is to apply a shift to a 5-axis path if shift MISC R is turned on. So we have the potential to open up kind of 3 extra spots if we choose not to use that shift MISC R, but then we also want to make sure that we comment out that variable, or at least put a note in there that says, hey, don't turn this on because we're using MR7, 8, and 9 for something else. Yeah, we can talk about some formatting things, Mike. Typically we cover that kind of stuff in the basic post class, but as we get into modifying the actual output code, it wouldn't hurt to do a refresher on both format statements and format assignments. Yeah, no worries. A lot of people haven't taken it. Top map is for our tilted work plane, and that will be done in the last section of class. So yes, we are going to cover tilted work plane. That will be kind of the last week of class. Yeah, that's one of the more advanced functions that we'll actually get into. TCP, Jeremy, honestly, we just probably won't have time in this class to get into it. I can show you where the different codes normally come out, but the thing is you have to worry about changing the machine mode and resetting a bunch of internal variables, and I know it's highly interesting to you. Potentially, man. I mean, we can certainly talk about it. It's, yeah. I'm not opposed to that. So, cool. All right, guys.